Hey, you tens. Welcome to exercise 19.2, where we begin circle theorems. And we take a look at all the key terminologies when we look at circle geometry and also the key proofs. So firstly, a circle is a set of points that lie a fixed distance from the center, which is what we call, or what we label with O. And then the fixed distance is what we call the radius, where the center to the outside of the circle or the circumference is always going to be the same. Let's talk about theorems. So when we have a theorem, it's aimed to prove at something. And so the proofs are often built upon congruent triangles and the proofs that we learned back in measurement. So when we proof a theorem, it's actually information which is built upon previous proofs. Okay, so for example, one theorem for circle geometry might require the proofs of the first two theorems that we learned. Okay, and there's going to be a lot of proofs, and the reason why we do this is so that we basically have evidence of our work. But enough about proofs and theorems. We're going to take a look at that more specifically in detail. Let's take a look at the key circle terminology. So the first one is a center, which represented by O is the center of the circle, or also known as like the origin. Circumference is the outside of the circle or the circle's perimeter, or the circle's edge, the only edge of a circle. The radius is from the center to the outside of the circle, as we know from measurement. And the diameter is when we have a line which splits through the circle completely, which is also double the radius, or the radius is half of the diameter. A chord is when we have just any random line which doesn't cross through the origin, otherwise it'd be called the diameter. So a chord is a straight line from one point of the circumference to the other, keynote straight line. And then we've also got a segment, which is what happens after the chord has split the circle into two segments, a small one and then a larger one if this chord is at the top of the circle, respectively, as we can see. Lastly, we've got a sector, which is like a pie or a cake or whatever being cut out. Okay, so segment has two radii. And then we've obviously done the calculation of the circumference of the sector. And then lastly, the arc, which is a certain portion of the circumference, big or small, doesn't matter. Last two, we've got tangent, which means to touch in Latin, which is a line that touches only one point in the circle, circle's edge, or the circle's circumference. And keynote, it has to be a straight line. A secant is a chord which is extended outside of the circle. Right, let's take a look at the first theorem. So what you notice is the theorems all have a code. So theorem one says, okay, in the diagram at the right, chords AC and BC form the angle ACB. Arc AB has subtended angle ACB. Long, complicated words, long story short, without looking too much into the proof, if we have two chords, A and C and B and C, the angle at C is going to be half of the angle, half of the angle subtended, or the distance from A to B. So this distance here on the angle is going to be half of the AB arc's distance. But let's look at better diagrams. So this diagram is a bit better. So when we send it to the origin, so a good way of remembering theorem one is like navigation arrow. So navigation arrow. Let's not complicate things. So all it's saying is PRQ, this angle here, okay, is half of POQ. So PRQ, this angle, that looks like a right angle. Is half of the angle at POQ. Okay, so long story short, this here is half of this here, or this here is 2 times the size of the one touching the circumference. And why is that? It's the interior and exterior angles of a triangle. So long story short, without having to do the algebra, we split this little triangle into 2, or sorry, this little quadrilateral into 2, forming 2 congruent triangles, which means I guess XY is going to add up to just exactly half of the angle at the origin. So that's theorem 1. Theorem 2. So here what we have is a situation where we've got think of like Star Wars and those battleships. What are they called? Anyway, like the starships. Or I can't remember what they're called, but or the Paul George symbol. If you're like into sneakers. But anyway, so all the angles that have their vertex on the circumference and are subtended by the same arc are equal, meaning these angles, so this angle here, this angle here, and this angle here, all the same. All right. Assuming they are joint here at the origin. Okay, so the graph's not very detailed. So yeah, let's not overcomplicate it with this one. So again, these angles are all going to be the same. Don't let the illusion of a small triangle and a big triangle fool you. Okay. Again, the proof here we won't worry too much about. Okay, so all these S, P, Q, and R, all the same angles. Right, let's have a go at using theorems 1 and 2. Okay, so we can figure out X. X is equal to 46 degrees using theorem 2. That's not how you spell theorem. No. Now we're back. Let's try and draw that Paul George symbol. Okay. So it's like oh, that looks terrible. You know what I mean by theorem 2. Okay. So the reason being is angle X here is going to be the same as this 46-degree angle. Again, because we've got an origin, and when the chords align, they're going to be the same. And then using theorem 1, we can find y. Okay, so theorem 1, we've got y as double whatever the angles touching the circumference is, which is 46, which is going to be 92 degrees. Okay, and this here is, I can't spell theorem. Right, so that's the first 2 theorems. There's about 13, 14, or 15 of them that we have to get through this topic. It's not going to be ideal going through the proofs right now. Okay, so giving reasons, just give theorem 1 and 2. That's plenty for reasons for now. Okay, the proofs in themselves is like a whole nother unit, and we might not have time for right now. All right, so theorem 3, angles subtended by the diameter, that is angles in a semicircle, are right angles. So what that means is in the diagram at the right, PQ is the diameter. Okay, so PQ is the diameter, as we can see right here. And so angles it's not rubbing it. A, B, and C are right angles. This theorem is in fact a special case of theorem 1. So notice how theorem 3 is built off theorem 1. We've got the proof here. So POQ, as we know, is the diameter, and that's a straight line of 180 degrees. So if that's 180 degrees, let S refer to the angle at the circumference subtended by the diameter. In the figure, S could be at the points where A, B, and C are represented. So it doesn't matter where, but A, B, and C, they're going to be called S, which is 90 degrees. So angle PSQ is 90 degrees at the circumference. The angle at the circumference is half the angle at the center, as we learned earlier. Okay, so with theorem 1, we knew this angle here is always going to be half of the angle in the center. And so that is why angles C, angle B, angle A, doesn't matter where it branches off, is always a 90-degree angle. Now, let's take a look at a construction of a tangent. This doesn't really bother me too much because you can draw a tangent line anywhere that just touches the circle. Doesn't have to be completely vertical and horizontal. Like I could draw a tangent like, oh, damn, I'm trying to do this freehand on a computer. Let me try again. I could draw a tangent like this. Let's pretend it just touched the circle once. And this could be completely a right angle as well. So it doesn't have to be perfectly vertical, horizontal. It can be diagonal and any other angle it likes. But whenever a tangent connects to the circle, okay, that connection point is going to be a right angle. All right. And that's what we call the tangent to be perpendicular to the radius. Okay, and then diagonal theorem 4, you can see this little tangent line with the perpendicular line as the code. Previously, up here, we had the right angle with the semicircle. So, find the values of the pro-numerals in the diagram at the right, giving a reason for your answer. So just using theorems. Okay, so here we've got S equals to 90 degrees because that's the tangent point. So that's theorem 4. And then we've got Z equals to 90 degrees as well because of theorem 3, where anything or any angle on the opposite side of the origin that's closest to the circumference is going to be half of the angle at the origin, which is 180 here. So that means Z has to be 90 according to theorem 3. Right, theorem 5. So the angle formed by two tangents meeting at an external point is bisected by a straight line joining the center of the circle to that external point. So the external point here is S. The tangent lines we have running past R and T. Okay, and then the bisecting line is from O to S. All it's saying is, well, we know R and T, that interior angle is going to be 90 degrees according to theorem 4. And then, well, the rest of the triangle has to add up to 180. So given whatever angle we're given, okay, we can problem solve for the angle at O and the angles at S. Here's a nice little proof. Again, we're looking at congruent triangles and why they are the way they are, okay? So example 3, find the missing pronumerals using Theorem 5. So they tell us 68 degrees is the angle at O. So therefore we know R, it's lowercase. And it won't rub out. There we go. The angle at R is going to be 90 degrees, according to Theorem 5. The angle at S is also going to be 90 degrees because of Theorem 5. Okay, so if we look back here, you've got two tangents. Actually, you could probably even say Theorem 4, can't you? Right, because it's a right angle. So let's go with Theorem 4. It's just weird. It's not letting me rub it. There we go. So Theorem 4, Theorem 4. Okay, so now that we know that's a right angle, this here's a right angle. We know, therefore, T must equal 180 take away 90 take away 68, which is going to be what is that, 32? So 90 plus 68 is 158. No, it's going to be 22. And so if T is 22 degrees, you can also assume U is going to be 22 degrees as well. All right, and then lastly, equals 68 degrees because it's, I guess, corresponding to its counterpart. Since U is 22, S is 90, for this triangle to add up to 180, we need this Q value angle to be 68 degrees. All right, and then let's see if this fits Theorem 5. So Theorem 5 said, well, Theorem 5 is essentially two Theorem 4s. So the angle formed by two tangents meeting at an external point is bisected by a straight line joining the center of the circle to that external point. It doesn't actually help with our proof. It's just Theorem 5 essentially is two sets of Theorem 4s. That is all for exercise 19.2. Have a go and let me know how you go. Thanks, everyone.